Hello, let's continue our Sudoku adventure with Products and Sums by James Kopp. So we have normal 6x6 Sudoku rules, so in each row, each column, and each 2x3 box, we are placing the digits 1 to 6 exactly once each. We also have these red lines in the grid. These are product and sum lines. So the sum of the digits on the line equals the product of the digits. So if we were to ignore Sudoku rules for a second, which we're not allowed to do in the puzzle, but if we ignore it and we do our example of 1, 1, 1, 2, 5, if we were to sum all of these, we'd get 1 plus 1 plus 1, that's 3, plus another 2 is 5, plus 5 is 10. So the sum is 10. Now what's the product? 1 times 1 times 1 times 2 times 5. The ones can be ignored, so we do 2 times 5, and that's 10. So 10 equals 10, so that would be a valid way to fill this line if we didn't break Sudoku rules here. So maybe like no, these can't be 2, this can't be 2 or 5. So maybe a 5 here and a 1 here. So this would be one way to fill it. Cool. And that's it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself. And I'm going to get started right now. All right. We need to think about this constraint clearly. So the first thing I want to think about is what pairs of digits just on their own. So like what goes on this line, right? What are two digits on their own whose sum and product are equal? And I'm pretty sure 2 is the only way to do that. 2 and 2 is the only way to do that. But we could try to prove that. Basically what we've got is an equation. I've got my pen tool here out. So forgive my mouse handwriting, but we've got x plus y is equal to xy, where both x and y are between 1 and 6, integers between 1 and 6. So we can prove here that 2 works, because 2 plus 2 equals 2 times 2, right? One thing we could do is we could move one of the digits to the other side. So we can do x, just subtract y from both sides. I don't know if this is helpful, sorry, but x equals xy minus y. I moved y to the other side. Oops, moved y to the other side. And so now we can regroup by pulling the y out. So x equals, if we pull the y out, then we get y times x minus 1. So we need x to equal y times x minus 1. And because this is symmetric, we know the same thing, that y is equal to x times y minus 1, for what it's worth. So we can divide by x minus 1. So the only way we can do that division is if x isn't 1. But we can prove that 1 doesn't work very easily. Because if x was 1, then that means 1 plus y equals y, which is never true. So we don't need to worry about that part. But what I will say is that we can divide by x. We get x over x minus 1 is equal to y. So whatever x is, we divide it by x minus 1, and that has to equal y. So if we go through all the possibilities for x, we could then see what y ends up being. And since y needs to be an integer, we can see what works. So if x was, we can't make x 1, where we prove 1 doesn't work. If x was 2, we'd do 2 over 1. So y would be 2. So 2 and 2 works. If x was 3, we'd be doing 3 halves. That doesn't work. Yeah, so that's never going to be integer other than 2, right? An integer is never divisible by 1 minus itself unless you're 2. We can't do 3 halves or 4 thirds or 5 fourths or 6 fifths. So the only thing that works is 2 and 2. That was kind of fun to prove. I mean, we kind of already knew that was the case, but so these 2's look up. This 2 looks in. That places a 2 here. 2's in one of these 2. It puts it on the line. 2's in one of these 2. That puts it on the line. So that probably helps us, knowing that there's a 2 on the line. So let's think about this. We'll just get bigger and bigger. Let's think about the 3 length. So the question is, are we allowed to omit a 1? Like our example is 1, 1, 1, 2, 5, right? It feels like we got to include a lot of 1s in order to balance the addition with the product with the sum. Because one leaves the product alone, whereas it increases our sum. And our product is generally going to outpace our sum. So, I mean, I already know that 1 plus 2 plus 3 is 6, and 1 times 2 times 3 is 6. That's kind of like the perfect number thing. So we know 1, 2, 3 works, but I think what we can think about is like if we omit the 1, then we have to do 2, 3, 4. And 2, 3, 4 is going to sum to way less than the product. So I just don't think that that's going to happen. I think we have to include a 1. And it just gets worse as you make the digits bigger because adding a multiplier is going to be adding way more than 1. So adding 1 to any of the digits is going to add way more than 1 to the other side. Adding 1 to the sum adds way more than 1 to the product. So we have to include a 1 here, is my point. And then I think this needs 2 1s. So this is going to be a 1, and this is going to be a 1. That's the only way to put 2 1s on here. And so that makes this a 1-2 pair. And with the 1-2 pair, I'm pretty sure this can only be a 3. I don't even know if we need to prove that, but I guess we could write out an equation if we wanted to prove it. So we could say that the sum we know is going to be 3 plus, I forgot to put the plus, I just wrote x. 3 plus x is our sum, and our product is going to be 2 times x, because the 1 doesn't get counted, or the 1 does nothing to the product. So if we subtract x from both sides, we get x is 3. That's the only solution. So that's our 3. So that makes this 4, 5, 6. Makes this 4, 5, 6. So we can do the equation for this one as well. Might as well. So what we have is we have 4 plus x. 1 plus 1 plus 2 plus x. So that's 4 plus x. Excuse my horrible mouse handwriting. Is equal to the product is going to be 2 times x. So if we subtract x from both sides, we get x is 4. So this is a 2, 4 pair, which means that's not a 4. In fact, this 5 looking in makes it a 5. These can't be 5s. How much Sudoku can we do before we do the long line? 3, 6 here. But actually, the long line, we know it needs 3 1s on it, so we should place those. Because we're not, again, we can't use 3 digits to sum to equal 3 digits as the product. It's just not going to happen. So this is our 1, this is our 1, and this is our 1. This one looks down, giving us 2 and 1. That gives us 4 and 2. That's not a 4. I guess this is 3, 5, 6. Maybe we should think about this line. We know what this digit is. Oh, sorry, not 6. This is a 4. And these 2 digits are a 3, 6 pair. Oops, 3, 6 pair. This is 1, 2. We need 3, 5, 6. It's not a 3. So one thing we know is that this doesn't have a 2 on it. So we can't use the 1, 1, 1, 2, 5 option. So there has to be another option. So basically what we're saying is that 3, the 3 1s is a 3, a sum, plus x plus y. Right, if we make this x and that y, that's going to equal x times y. And so what we can do is we can just test the 3, 5, and 6. That's an option here as our x, and then see what works for y. You know, we may be able to move this around a little bit to help. Maybe if I'm going to be filling into x, we could get a single use of y to help us solve for y. So we could do 3 plus x is equal to, and on this side we subtracted y from both sides. So it's going to be xy minus y. And now we can regroup. We can pull the y out. So 3 plus x is equal to y times x minus 1. And so now my idea is to plug these digits into x. And that'll tell us what y is once we rearrange a little bit. I mean, I could divide by x minus 1. So basically what we're doing is 3 plus x divided by x minus 1. And that's going to be y. So if x is 3, that's going to be 6 divided by 2. So y would be 3. So 3 and 3 works. With a 5, we'd be doing 5 plus 3 is 8. Divided by 4, it would have to be a 2. And so we knew 5, 2 worked, but this can't be a 2. So this isn't a 5. And then 6 plus 3 is 9. Divided by 5 is 9/5. So we can't put 9/5 there. So our only option, actually, is to put 3 here and 3 here. We can clear out our pen tool now. I don't think we're going to need it again. All right, that's 6, that's 3. These can't be 3s. That's a 5, 6 pair. This is our 4 for the box. This is a 6 for the column. We get 4 and 6 here. That gives us 5 and 6 and 5 and 4. We get our 6 and 3 and 6. We need a, oopsie, sorry. We need a 3 in here. That makes this a 5. That makes this a 4, and this is a 5. All right. Cool puzzle, James. I'm not sure how rigorous I was, but I feel like there are some, you don't have to be super rigorous to prove that 3 digits aren't going to work. You need a bunch of ones on these lines. So that you only have 2 non-ones on each line. I'm pretty sure that's going to be the case. And then this being 2 times 2, I think I actually did prove that that was the only one that would work. All right, cool. Well, let me know how you did. And if you enjoyed this, why don't leave a like, subscribe, and a kind comment below.